So you have already watched the first part, right? Right? You guys have already. Yes. Okay. It's a very important technique called pulse rotation. So let me start with this. So this technique, when you have a long path, somehow you connect this to here, and connect this to here to create a Hamiltonian cycle. It's called a cycle exchange. And also there is a way, if you have a long path, for example, you start from long path, and if Vn joins some Vi minus 1, and here we have Vi, we consider this path start from V0 until Vi minus 1, and you go to Vn, and you come back, and you finish at the vertex Vi to obtain another path. This is also called so-called pulsar rotation. So it gives different passes. These are essentially the same thing. So today I'm going to, in the second lecture, I'm going to tell you about some sufficient conditions. Like I said in the first lecture, that for Hamiltonian cycles, there is no both sufficient and necessary conditions. So here, let me introduce some sufficient conditions, and they are not, in general, necessary. So for example, if G is a bipartite graph, if G is a bipartite graph, for example, two parts, bipartition L union with R. Okay? Suppose G is a bipartite graph. And then, and suppose G has a Hamiltonian cycle. Admits a Hamiltonian cycle. Then the two parts must have the same size. So the size of L must equal to the size of R. That's the necessary conditions. Sufficient or necessary? So necessary conditions. Okay. Necessary conditions. Okay. So this is actually I leave this in one of your list problems. If you have a bipartite graph on the two parts L and R, and if you have find some Hamiltonian cycle, then it's clear that half of the vertices belong to L and half of the vertices belong to R. Okay, so it means that the two parts must have the same size. Okay. This is a kind of simple, but in fact you can consider other similar things. If you are looking at a Hamiltonian path on a bipartite graph. So let me put 1.2. If G is a bipartite graph, on a bipartition, again, L union with R. And suppose G admits a Hamiltonian path instead of a Hamiltonian cycle, then something similar must happen. So the difference of the two sides, they must smaller or equal to 1. So you cannot have a difference of 2 in two parts. Is it clear? So for example, you have L here and you have R here. And suppose you have a Hamiltonian path. At the most worst situation is that you start from here and maybe you do this, and you end up in the same side. And in this situation, for example, in this example I draw, there are 4 vertices on the left and there are 5 vertices on the right. So in the worst situation, the size of L equals the size of R equals to the size of L plus 1. Okay? So there's no way that the size of one side is greater than the size of another side plus 2. This cannot happen. So this is the conclusion. The difference of the two sizes is at most 1. Okay? Let's see an interesting application of this. It's a Olympiad problem. So I think it's very interesting. So consider a chessboard. So problem. Here I have a chessboard. And okay, so it's a kind of a long chessboard. So you have, let me count, 3, 4, 5, 6, 7. So 2, 3, 4, 5, 6, 7. And I draw this. So it's a strange chessboard. What I'm drawing is this. I think I'm fine. Okay? Okay. So there is a knight here. Okay, here. Standing here. So I'm asking, so here stands a knight. So the question is it possible for this knight to move according its rule, of course, so with respect to its moving rule, to move such that it goes to every position. It goes to every position and exactly once. For each position. Is that possible? I don't think it's very very simple to look to realize that this is actually a problem about the Hamiltonian path. So what happens is we have to do this. We want to color the board in such a way. So for example, I color this black, I color this part black, I color this position black, and the second line I color this position black, and I color this position black. So I color this, I color this, okay, and then I would color this, color this, color this one, and color this one, and finally I color. You see, I color this one. So here it's a white board. Here I color this one and I color this one. So how does a knight move? So this knight, it can move to this position or this position. So remember, if you never play chess, there is a problem. So at least I don't know how to play it well, but at least I know the rules. Knight can move from here to here. Okay, he can only move from here to here. So starting from here, he can only move to this position, position 1 or position 2. So what happens is that every time he moves, he must move from a white position to a black position, or he move from black position to a white position. Next time he can move to here or to here. Okay? So if you draw a graph about all the possible positions, you find that the number of white positions is, I think, is 16. So you can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And the number of black positions is 14. Okay? So that means that the difference is 2 by the proposition we just stated here, 1.2. The graph admits no Hamiltonian path. So that's it. So if you translate the situation back, it exactly means that you cannot do it. So the answer is no. Okay? So the answer is no. You cannot do it. If you can do it, what you have done is exactly you find a Hamiltonian path. It's not necessary that you arrive at the same position in the end. So you don't care about a cycle, but you are looking for a Hamiltonian path. And in this situation, such a path does not exist. Okay? Okay? I think it's a fairly simple problem. But the difficult part is translate the problem into a graph theory problem. Everyone is with me, right? You have some questions? Okay, thank you. So again, this is a problem. This is a situation. The difficult part is how to translate. So we have dealt with this kind of problem even since the first lecture. So we have to. I think this requires some experiences. But once you have been able to translate the problem into a graph theory problem, so the tools and the theories needed is just it's not many. There are not many things you have to know. Okay. So we move on. So we want to look at the condition of Aula's condition, the Aula's theorem into some depths. So we can do even more. So recall Aula's theorem. So if remember, I want to write this in another way. If UV is a non-edge, so it's not an edge, it's a non-edge in G, and the degree sum du plus dv is at least n. Okay. remember, what we have proved is that if UV is a non-edge, and we have a path. So suppose we have a path starting from U and at V, and the length of the path it goes through all the vertices. It's a Hamiltonian path. And at the same time, du plus dv is at least n. Then we can find Hamiltonian cycle. Okay? So I want to state this theorem in another way. So if there is a non-edge UV with this condition, then G, the graph G, remember UV is not an edge of G. The graph G admits Hamiltonian cycle if and only if G plus UV admits a Hamiltonian cycle. Okay? Do you agree? So this is actually another equivalent statement. It's the same thing with the Gauss theorem. So what happens is if G admits Hamiltonian cycle somewhere, of course, if you add another edge to G, it admits Hamiltonian cycle. But with this condition, if G plus UV admits Hamiltonian cycle, it means that if you delete UV, you have a Hamiltonian path. And with this Hamiltonian path and this condition, you can construct this cycle. So another cycle. It's not the first cycle. And this cycle does not use edge UV. Okay? So the proof is left as an exercise. It's not that bad. Okay? It's exactly the same thing with the theorem we proved. But what is interesting about this is that using this, it inspires some people to prove to give a very reasonable definition. We call the Hamiltonian closure Hamiltonian closure of G, of a graph G, denoted C of G, closure of G. What is it? Is the graph obtained in the following way. It has the same vertex set with G, so CG has the same vertex set with G, and you have to add by adding new edges. For example, UV to G, wherever the sum degree is at least n. So you keep adding until there are no such edges. Okay? So what is going on? What's going on? For example, I don't know. I have no very specific example. But what happens is that if you have some graph, for example C5, well, C5 is not very good because the degree of this guy is 2. So let's say this C5 plus one edge. we have V1, V2, V3, V4, and V5. So this graph I call G. Okay, so maybe okay, so the degree of this guy is 3, and the degree of V2 is 2. So in particular, their sum, the degree sum of these two vertices is 5. Okay, in this case, I can add this edge into my graph, and I can keep doing this. So whenever I have this has degree 3, and this has degree 2. I can draw this. So next step, I would draw this new edge. So let me. Okay, I keep doing this. In fact, as for this example, in the end, I get K5, which is a complete graph on 5 vertices. It's not necessarily happening for every time. Okay, so I'm saying that if I start from G and I keep doing this, in the end, I will find the C of G, the closure of G. In this case, the closure of G is equal to exactly the complete graph on 5 vertices. So there is a question, there is a problem here. Are you sure if you choose, so given 2 different people, maybe they decide to choose different edges. So are you sure that in the end you get the same graph? So a question. With the above process, is the final graph C of G well defined? Because we want to define this as the closure of G. If you use choose different orders of all these edges and you end up with different graphs, then this graph is not well defined. Okay? So it turns out it is well defined. So let me prove this proposition. So the closure C of G is always well defined, is well defined. Okay? Let me prove this. How to do this? Suppose starting from G, maybe we add some sequence of edges, maybe in order, but the order in the end is not so important. We add edges E1, E2, etc. until EP to become G1. Okay, to become a graph G1. And we have to stop here because there is no edge to add. You cannot find another edge satisfying that the degree sum is at least n. So you stop. And suppose we can also, suppose if we start from G and add edges F1, F2, etc. until FQ to become G2. And what we are trying to do. So this is the same process, but we don't know if the order of the edges. So another person did, 2 people do this in different ways, possibly. Okay, the first person decide to add E1, E2 until EP, and then he obtains the graph G1. And the second person starting from G always, he decided to add f1, f2 until fq, and he obtained g2, and he has to stop because there is no other non-edges whose two under vertices satisfy the condition. So this is the only situation you can stop. But what we are trying to prove is that g1 equals g2. Okay, so it suffice to show that, for example, one is contained in another, because you see, because they are kind of symmetric. If you are able to prove that G2 is contained in G1, and basically the same argument gives you G1 is contained in G2, there are no differences. Okay, so you pick G1 and G2, you are trying to prove arbitrarily, and you are trying to prove G2 is contained in G1. So for this, we will start. We observe, we make an observation. Observe that if UV is a non-edge, so does not belong to G. It does not belong to the graph G, and at some point, when I say at some point, I mean during the process. For example, I already added some edges, and I look at the graph. I have updated the graph G to some point after in the middle of the whole process, and at this point, the degree sum is greater or equal than n. Then, what I can conclude is that in the end, eventually, this edge UV will be added. Okay? So once the degree sum is greater than n, then you finish the whole process until you cannot do this, because this pair has already satisfied our condition. So maybe next step we don't choose it, but at some point in the future we have to choose it. Otherwise we will not stop the process. We stop the process only when there is no such pair satisfying this condition. So this observation says that, okay, if you have some non-edge with this condition, in the future this edge has to be added in both processes. Either in the first process when you're adding this E1, E2s, or in the second process when you are adding F1, F2s. So there is no difference. So with this observation, what can we do? So therefore, let's look at F1. We know that F1 is the first edge added to G2. Okay, so here, F1. So it can be added to the graph G2 means what? Means, remember, at the beginning, the graph is the same. So we start from G in both processes. F1 can be added to the graph G2 means that, for example, F1 equals U1 V1, means that D U1 plus D V1. So let's put it U1 V1. So D U1 plus D V1 is at least n. Okay? So it means what? It means that by the observation, U1 V1 must be added to G in the first process also. In the first process. Okay, so this argument is not long, but it takes some time for you to understand. So f1 is the first edge added to the in the second process. But since you can add it, it means that the degree sum is at least n. So it implies, by the observation, it implies that u1 v1 also has to be added in the first process. It must equal to some ek for some k. It is not necessarily equal to E1, but it must equal to some ek in the process by the observation. So inductively, so here I have proved that f1 actually is 1 of ei. Now inductively, I would like to use induction. Suppose that f1, f2 until fi, okay, they belong to this set of e1, e2 until ep. Suppose we already have this, and I look at I plus 1. Again, look at f plus 1 and also consider the graph G plus E1, E2 until Fi. In this graph, since the edge Fi plus 1 can be added, implies that in this graph, for example, this edge equals ui plus 1, vi plus 1. So since this edge can be added, it means that d ui plus 1 plus d vi plus 1 is at least n in this graph. Okay? But all these edges belong to this edge set by induction hypothesis. So it means that in the process of in the first process, it means that G plus F1, E1, E2 until some ek, for example, must contain all these F1, F2 plus Fi. And in particular, in this graph, for some large k, Fi plus 1, so this condition holds also. So star also holds. So by the observation, eventually I plus 1 must be added. Okay? So by induction, we have proved that the whole G1, which equals G plus E1, the whole G2, which equals G1, G plus F1, F2 until FQ, this is a subset of G1. Okay? So, any questions? . basically what happens is that you have a set of edges E1, E2 until EP. And you get another set of vertices F1, F2 until FQ. We are trying to prove that these two sets of edges, they are the same. We are trying to prove that they are the same. And inductively, we pick one by one edges from the F set. And we prove that all of them belong to the first set. And by the reason of symmetry, it's the same thing if you pick one by one edges from the first set. You can prove that they all belong to the second set also. You can try this, but it's the same argument. Okay? So this proposition shows that the closure of G is actually well defined. So with this, there is the theorem saying that G admits a Hamiltonian cycle if and only if the closure of G admits a Hamiltonian cycle. Okay, because every step when you add a vertex, an edge, in the whole process of forming a closure, every step you doesn't change. So remember this all theorem. Whenever this condition is satisfied, then every step when you add an edge of this UV, the graph of whether or not the graph admits Hamiltonian cycle, this property does not change. Okay? So it's pretty nice. Okay. There is so this is the main topic of today's second part. But I want to introduce another thing without proof. So there is another set of conditions which has a relation with our next lecture. So let's define something called the connectivity of a graph. You can imagine a graph is connected, but somehow there is a vertex here and all other vertex is here and all other vertex here. So this V is very special in the sense that if you delete this vertex, the graph becomes disconnected. Okay? In this case, this vertex is usually called a cut vertex. So the connectivity, so in general you can put, for example, 3 vertices. And they are saying, okay, if I delete 3 vertices, then the whole graph will become disconnected. So, but if the graph has a cycle, for example, here I have a cycle, the whole graph is a cycle. No matter which vertex you delete, you cannot make the whole graph disconnected. But if you delete 2 vertices, and the whole graph become disconnected. Okay? So there is a condition, this definition, which will be introduced next week. It's called connectivity of graph. Usually we use kappa of G to denote this number. The connectivity of a graph, kappa of G. By definition, it is the largest number, the largest integer, let's say k, largest k, such that there exists no set with k minus 1 vertices such that by deleting them, what I'm saying, yeah. So there is no set with k minus 1 vertices, such that by deleting them, the graph becomes disconnected. Okay. For example, a cycle has connectivity 2, because you cannot delete one vertex to make the cycle disconnected. So imagine you have some graph. You cannot delete 3 vertices to make it disconnected. Then the connectivity of the graph is at least 4. And the largest number is the connectivity of the graph. So the connectivity kappa of G is the largest integer k, such that you cannot find k minus 1 vertices. The removal of all these k minus 1 vertices makes your graph disconnected. So this is a definition I introduced now, but the next lecture we will study this in more depth. But another definition, which is easier, so we already have seen this, in fact, alpha of G, the independent number. The independent number which is the size of the largest independent set of G. So you can imagine that the connectivity tells you how connected is the graph. So with the connectivity higher, for example, connectivity is 3 or 4, it means that your graph is highly connected. And the independent number is, can you find a set containing no edge at all, and how large can you find it? So the largest integer such that the graph meets a subset with no edge and with this size of vertices. So here, with these two conditions, we have this theorem. Subtle and Erdish, saying that if the connectivity of G is greater or equal than the independent number of G, then G admits Hamiltonian cycle. Okay? So it's I think it looks very nice, very beautiful theorem. And the proof is not so difficult. I will not give a proof of this theorem. In fact, I will put this as in your next list as the special. So in every list, I will put one special exercise which is more difficult than others. So I will give some hints and encourage you to solve this theorem by yourself in the next list. Okay? So here is the plan for today. Let me finish the recording and